thing about a bus, and that throws off a lot of people, is the desire to point to something and say, this is my bus. We're engineers, very practical, pragmatic people, and it's very useful for us to kind of come to a given architecture and kind of walk up and pat it on the side and say, you know, this is my bus. It's equally comforting to a manager to be able to point to a nice big fat box that they just spent several $100,000 on and say, take a look at my bus. But the thing is that that's often more of a broker. So the thing that you can actually reach out and touch to a large extent is not a bus. Which throws a lot of people off because it's the kind of thing, it's the most intuitive thing that you could think about is a machine where something runs. And it connects to a bunch of other things, and a bunch of things connect to it, and therefore you've got a bus. Nice centralized box in the middle of your architecture. The problem with that is that while it's intuitive, it points us in the wrong direction. The best metaphor that I can give you for a bus is Ethernet. So imagine walking up to Cisco and saying, hi there, I'd like to buy an Ethernet, please. And the sales guy from Cisco kind of looks at you sideways and says, what kind of Ethernet would you like, sir? Oh, I don't know. A good one. A fast one. A big one. You know, a scalable Ethernet. After a while, the guy from Cisco realizes that this customer has no idea what he's talking about. Would you like some Ethernet cable, sir? We have very long Ethernet cable. I said, oh, no, I don't want cable. I want Ethernet software. And where would you like to put this software, sir? Oh, I don't know, on a big box in the middle of everything. And have everything connect to my centralized Ethernet. Ethernet doesn't work that way. But for one reason or another, people kind of say service buses should work that way. Ethernet has a bunch of distributed parts to it. Now, a lot of people, when starting to use NServiceBus, say, oh, I don't like the fact that I have to have MSMQ installed on every machine. And I can understand that sentiment. But by the same token, when you go and buy yourself an Ethernet, when your Ethernet vendor says, and you will need to put this physical card in each one of your machines that would like to connect to the Ethernet, you don't see people complaining. It's perfectly acceptable to have an Ethernet card in a machine. Otherwise, how else could it work in the Ethernet world? There is something that needs to represent Ethernet. Something physical on every box. And you need cables that connect it from one place to another. And not every topology looks the same, right? It takes a fair deal of understanding and knowledge based on your network engineer's part to decide how to set up your network topology. Which things go on which subnet, how to handle remote sites. Not everything is the same speed, so your LAN is one speed and your WAN is another speed. It's something that we've gotten so accustomed to, it's just always there, that we kind of say, okay, well, yeah, that's Ethernet. But we expect a service bus to be something else, kind of like a broker, just that we want it to be distributed. But we're not exactly sure what that means. So probably the most, how's it going? So the most useful concept to think about when envisioning what it is that a service bus does is to take into account that concept of Ethernet. There's a software component to it, right? Inside our operating system, there is the OSI stack that describes the protocols that we can use. As a part of that protocol, there is the concept of how do we identify things. Can you walk up to any old Ethernet and tell me where a given IP address is just by looking at the machines from the outside? But no, you can't, because an IP address isn't a physical construct, not by itself. IP address is an abstraction created in the language of Ethernet that says, let's all agree on a certain way of identifying ourselves. And we'll make sure that everybody, if they have an IP address, if they have a name, that nobody else will have that same name. It's an agreement. It's a protocol. You can't see an IP address on the copper wire. There is no physical IP address baked into anything. But it is necessary to have that concept of logical identity, the IP address, for any kind of Ethernet communication to work. Similar when we're talking about a bus. We need to have this concept of naming things. What is this logical thing, and what name do we give it? And we need to ensure that there can only be one logical thing that is named the same way. Not necessarily talking about a physical representation. We may have multiple physical representations. We may have multiple Ethernets, multiple networks that are deployed side by side. Concept of an IP address and how we plan our network topology, that's the abstraction to look for when first approaching a service bus. What that means is that services are not so much a physical box. And it's one of the things that we expect to be able to load balance and to scale out our services. But that concept of identity is quite critical in any kind of thing that we're dealing with. So in this picture, identity is represented by color. We have the green name, and we have the purple/gray name. And things need to identify themselves in the language of a bus. Just like when you're sending a message out using TCP, you include information that says, who am I? And who am I talking to? Then there are pieces in the network topology that facilitate the communication between one name and another name. Right? If I say, okay, send this message, send this TCP packet to the machine or to the place that's called 128.196.0.0.25. There's nothing on the box itself, if you take away the Ethernet, that identifies it that way. It's a logical construct. Similarly with the service bus. So when I say, hi there, I'm green, I'd like to send a message to purple. We use that concept of identity, who am I and who would I like to talk to? Where the bus infrastructure deals with how do I propagate this packet of information to the target address. Where it's, at that level, it's still a logical construct. Ultimately, there needs to be a mapping to the physical that deals with, okay, physically, where is it? So that's what, when you're just starting with NServiceBus, to keep in mind that this is not about physical machine-to-machine communication, just like Ethernet is not about copper wire. When you're programming with Ethernet, you're not thinking about copper wires. You're working at that level of abstraction. When you're working with a service bus, look for a similar level of abstraction, of identity, because there has to be one identity, one concept of ownership for anything. Once you have that, a lot of other things tend to happen. So, number one, there is no assumption that a given identity exists in only one place. You can think about this from, in a web farm example. Clients, all the browsers that are making calls to your server farm, they have one well-known DNS that they contact, right? And that DNS is mapped to an IP address of a load balancer. Behind that load balancer are as many machines as you'd like. But from the client's perspective, it doesn't matter. It has one logical IP address that says, they told me to send the message here. Eventually, some other machine handles it. Same kind of idea with the service bus. They told me to send this message to purple. Just like it doesn't matter which web server in your server farm handles a given HTTP request, same thing happens in the land of a bus. All of the purple things are equivalent. We are purple. We are the web farm of your website. It doesn't matter where this message ends up, because we're all the same. So that level of load balancing, where does this message end up, is not so much an issue for the application developer. Just like when you're designing a web application, you're not concerned about, just a second, what's the IP address of this web server, and what's the IP address of that web server, and every single web server in your load-balanced farm. You don't bake that information into the browser JavaScript code that is making the call. I've got one well-known IP address, send it over there, eventually one of the machines that are all equivalent will pick it up, and it doesn't matter which. What's important is that they're all identified as being equivalent by having the same name in the concept of the bus. So ultimately, that's what the bus deals with. It says, you're green, you're going to ask me, the bus, your Ethernet, to contact purple. Send purple this message. And me as an Ethernet, I will get it to one of the purples that are there. Out of all the purples that told me that they are purple, I will get the message to one of them. So it's similar in that the naming, as you're already dealing with it in a load-balanced environment, the naming as being something that has to be representative of business logic. Just like you set up different DNS entries for different websites, though they may all be ultimately deployed on the same machines, the names of things matter a lot. The logical routing that says, I would like to contact this DNS versus that DNS. If both happen to be mapped to the same physical machine, so be it. It doesn't influence your application design. So a service bus is there to facilitate that kind of communication, to give you yet a higher level of abstraction in talking about your architecture, rather than being very much close to the metal, saying, well, I'm going to connect to this WCF service that's running on that machine. I'm going to connect to this WCF service that's running on that machine. Ultimately, the question is, but what's its name? What does it represent? So we need to have, first and foremost, that concept of naming. So that's the first part when we're talking about a service bus that indicates how different it is from things like BizTalk. And okay, please compare and contrast BizTalk and Ethernet. Say, well, you can't really talk about the comparison. They're two different tools designed for very different purposes. Similar with a service bus. It's an inherently distributed infrastructure that you will be deploying on multiple machines, just like you have an Ethernet card on every machine, that given that you follow its language, given that you work according to its protocol, it will be able to facilitate communication for you. The next part about a service bus, or about the buses in general, is that they're primarily concerned about events. But taking a step back from the concept of an event from the semantic sense, there's one thing that's actually very interesting about an event, no matter how you define it. There is no response to an event. There's nothing inherent that says, oh, I've published an event, but now I'm waiting for a response. If you're waiting for a response, you haven't actually published an event. You're not speaking the language of a bus. In Ethernet, is there a concept of a blocking call? Can you actually block your Ethernet card? Well, you can try, but it's breaking the rules of Ethernet. There's a TCP/IP request, and you can send out a bunch of other TCP/IP requests. There's nothing inherently blocking about TCP. And if no response ever comes from your TCP, so what? It doesn't hurt Ethernet. It doesn't undo what Ethernet is about. So that concept of making a request and waiting for a response in a blocking fashion, right, that I don't want to do anything else, not a concept of Ethernet, not a concept of events. So for an example of an event, order accepted. What is the response to the order accepted event? Well, there is none. Either the order was accepted or it wasn't. If it wasn't accepted, you wouldn't have published the event, so it's kind of meaningless to talk about that scenario. And if the order was accepted, what possible subscriber could undo that fact, could invalidate that request? There is none. Either the order was accepted, and that's the end of the story, or it wasn't, and the event wasn't published. That's the kind of communication that buses are there to support. It's not there to allow you to do anything and everything that you want. Just like the purpose of Ethernet is not to allow you to put any old electrical signal on copper wire. If you want to put any old electrical signal on copper wire, Ethernet is not the tool for you. It explicitly restricts your option, says, this is the protocol that we're going to talk in order to have any kind of meaningful conversation. Well, we have to agree. We're going to be talking now in English. Unless we agree which language we're talking about, communication won't work. We have to constrain our options. That's how buses are. And one of the things that we do, say, there is no inherent blocking response for any kind of communication. When you send out a message using a bus, that's it. It's a done deal. Maybe you'll get some other message back later that is correlated to your original request. Maybe you won't. Kind of like when you send somebody an email. You send them an email. You're hoping maybe they'll respond back. But you've got better things to do with your time than sit there and wait. It's not for synchronous blocking communication. That's not part of its protocol. Now, some people say, but wait a minute, what if I really want to do synchronous blocking request response? Fine. Don't use a service bus for that. That's not what it's for. Just like if you need to saw a piece of wood, don't use a hammer. Now, people have, and developers particularly, we love our tools. And the more things they do, the more that we love them. Which is why probably a lot of us, when growing up, had Swiss Army knives. Right? And the bigger the Swiss Army knife we had, the higher our social standing among our friends. It's, oh, yeah, yours has a screwdriver and a saw, but mine has, a barometer in it. Or mine has this. The more tools that you could have in the one package, the more powerful you felt. However, the bus actually takes a very different approach. Just like you wouldn't use a Swiss Army knife Well, you wouldn't even use it to build a doghouse, right? Even the smallest construction project around the house, you're not going to be using a Swiss Army knife. You can use it. Hammer, nails, screwdrivers, everything that you need, each tool standing alone, even for relatively small projects. Same thing here. Is that Service Bus is not supposed to do everything. It's not supposed to replace everything. If you want to do some synchronous client-to-server communication, hey, use WCF. Use a standard web service. If that's what you need, do it. There's lots of things that make use of synchronous communication, like ADO.NET. Maybe a lot of you don't think of ADO.NET as a synchronous RPC technology, but that's exactly what it is. I'm on my machine over here, and there's a database over there, and I'm going to do ADO.NET commands, RPC, with that box over there. That's fine. Nobody would be saying, no, you should replace all your ADO.NET code with a service bus. That'd be insane. But for some reason, we have this impression that we should replace synchronous WCF service calls with a service bus. Because, hey, they both have the word service in their name, which is just kind of a poor choice of words, and ultimately any word that you choose is going to be used by something else. So Service Bus is not supposed to handle everything in your architecture. It's not supposed to be the magical Swiss Army knife that solves all your problems for you. It's just one part of it. It doesn't replace ADO.NET, it does not replace synchronous WCF services. So understand you will have some cases where you're doing synchronous calls and then use the appropriate technology, and other cases where you are more interested in the ability to have a higher level of abstraction. So, for example, what are the uses of a service bus? What are the things that it does well? Well, I said events. Publishing and subscribing to events are things that synchronous RPC like WCF does not do. Or, in parentheses, it does not do it well. Anybody here written a publish, subscribe WCF service? Yes. Made sure to hold on to a reference to all your client proxies? No? Okay, you're done. You held on to the client proxies? Yes. You remember to refresh the client proxies after it faulted on you? Yes. You remember to do that in a multi-threaded fashion so you wouldn't run out of threads on your server? Yes? Excellent.
The hard way. Found out the hard way.
Excellent. Next thing to do. Did you handle durable messaging? Because you have to make sure that even if the client was down and the server crashed in the meantime, when the server comes up again, it has to propagate the message back. No, you didn't do that one.
Right, but it wasn't for that. Yes, I know. It was more like communication, so we're just broadcasting info on a pop-up.
Okay. There are a bunch of very difficult, intricate, complicated technical details in getting these two words, pub/sub, or if you want one word, pub/sub, to work. And a lot of the challenges have to do with the fact that you can't necessarily assume that when sending a message to the other party that the machine is up. You can't. Sure, it's up most of the time, and it runs on my machine. And even in the test lab, it usually works most of the time, except when we're running the load test. And then we stop the load test, bring all the machines back up online, rerun the load test, and then tell our boss everything works great. Just don't bring down any other machine. Unfortunately, and maybe I'll pause for a second and see. You ever get this little icon that says, critical Windows patch, requiring a restart? It turns out that we can't ensure that all the machines will be up and running all the time because, well, we get critical Microsoft service packs that we need to install. And it would be kind of unfortunate if every time that we did that, For any box in our system, we had to stop everybody. But that's ultimately the problem with synchronous RPC communication. The more synchronous RPC calls that we have, the more machines that all have to be online all at the same time. But unfortunately, as we know, it's practically impossible to ensure that all machines will be up all the time. And to make sure that when something goes down, we won't lose messages. It would be a very unfortunate state of affairs if I, as one service, I publish order accepted, and the shipping service just happened to be asleep at the time. Right? You go and order a book on Amazon.com, you got one service that says, order accepted, everything's great. And the shipping service wakes up again and says, what did I miss? But nobody remembers. Okay, so that book wasn't shipped. No big deal. Or we didn't bill that customer for that book. Oh well. We didn't want their money anyway. There are lots of problems in getting this communication to work such that even if machines are going up and down, we won't lose messages. And that's one of the things that the bus provides to us. It says, based on the fact that you're working at a higher level of abstraction, and the infrastructure is kind of like Ethernet. We have an Ethernet card on every machine, just like we have a bus queue on every machine. We have the ability to store stuff such that even if the target machine is down, we can have it stored, and we can remember that when we come back up again, that we need to pass order accepted over to the shipping service. So no messages, no events will be lost in the case of something crashing, which is a big bonus when you think about it. It's not the bonus that a lot of developers are used to, because when we're testing out our systems, we kind of bring all the processes up, cross our fingers, and click a button. And if everything works, we happily check in the code and say, yes, yeah, it works great. But making a system production ready such that, if not all the machines are working, communication will continue to happen, messages will not get lost, that all our data remains consistent, is a challenge. Unfortunately, it's the kind of challenge that nobody told developers that they should handle. Oh, just use WCF. It's great. Oh, I have no issue with WCF, but really there's only one WCF binding that has the chance of preserving messages in the case of one of the sides going down. That's the net MSMQ binding. Who here uses the net MSMQ binding with WCF? It's unfortunate that Microsoft didn't tell you that unless you use the net MSMQ binding, if one of your machines goes down, you may be losing data. But hey, I mean, you were losing data with ASMX Web Services before, so if it was good enough for you back then the various WSHTTP bindings should be good enough for you now. But that's interesting when you think about it. Developers are often very concerned about single points of failure. But the question is, that single call, it's not a single point of failure, right? How does it fail over? Where do you preserve its messages? That's why we need a queue on every box. Just like with Ethernet, that's why you need an Ethernet card on every box. Because without it, you can't communicate safely. So those are the two big things that NServiceBus is there to provide you. That kind of infrastructure that will give you safe communication, even when you're not sure about all the failure scenarios that you're going to be dealing with. It's infrastructure that's safe by default and will warn you when you've set it up the wrong way. Just like in Ethernet, if you come up with an IP address that somebody else is using, Ethernet will yell at you saying, I'm sorry, somebody else is already using this name. You can't use it. Similar, if you try to configure NServiceBus in such a way that you don't respect the naming rules, it'll throw up all sorts of warnings at you and says, no, I'm sorry, you can't have two publishers which are publishing the same message. You can't have two logical names that mean the same thing. So that's a large part of NServiceBus in terms of a concept, in terms of philosophy. And it takes some time to get used to, because it's not just like regular communication. You don't just get a proxy to something and call a method on it, because it may not even be there when the message is being sent. You can't assume that the other side is up and running.
Can I restart your computer?
All right, restart it. Mm-hmm. And that's exactly why machines need to be restarted every once in a while. But you wouldn't want the fact that, there's a pending WCF callback contract trying to communicate from your server to this machine to hang a thread on your server until 30 seconds later you have an HTTP timeout. It's kind of a good question. What would you do on the server after you had an HTTP timeout from trying to call back to a client? So, publish, subscribe, and service buses in general are a different concept than RPC programming. It's not there to give you the exact same programming semantics. Just like originally, when Ethernet came out, a bunch of people kind of looked at this and said, what do I do with this? Distributed programming. I said, what do you mean distributed programming? The only kind of distributed programming that we have is I wrote something to a floppy disk, took the floppy disk out of one machine, stuck it into another machine, and then ran a program there which read the file. That was one-way messaging, durable messaging, until we had Ethernet, right? Just passing around floppies all the time. That's how we got our original version of, Windows 95, right? Passing around copies of CDs. We didn't actually have the bandwidth to get it out over the network. Yeah. Mm-hmm. So the question was, how does this compare to the Java messaging specification, JMS technologies that are available on the Java side, for example, Sonic MQ or IBM MQ? There are certain similarities, but it's not, you don't see it on every single topology. So the default way that JMS technologies are deployed are as a broker. So you have your one big JMS server box, and you have a whole lot of spokes around it with a JMS client that are connecting to that centralized box. And then they're doing their communication with the box. But the assumption is, I am always connected to the centralized box. I'm not expected to do anything if I can't get connected to that centralized box. That's the broker topology that the vast majority of JMS technologies, which were originally called message brokers, not surprisingly, that's what they were built to support. Some of them, and quite a lot of them, support a federated model. In other words, we have multiple servers. And then we start talking about a setup that is quite a bit closer to what buses are. So you can deploy a JMS technology in a bus architectural style. Conversely, you can deploy it as a broker. There are some people that have worked very hard to deploy NServiceBus as a broker. Despite my best efforts to make it hard on them to do it, they still have managed to turn it into a broker. For all the reasons that I mentioned so far, the ability to have different machines operating at different points in time, not all machines up at the same time, to have the concept of naming, we need to move to a more bus approach. than a broker approach. So the broker concept is quite simple. It says you have a single box that if it goes down, nothing works, which is a decent kind of deployment technology, especially if you're a vendor that is selling licenses based on the numbers of cores that are there. There happen to be a lot of vendors that have that licensing model. However, when you move to the bus architectural style, for example, what we're using in NServiceBus with MSMQ, you have a little bus on every single box, actually alongside every single process. We're giving up?
We'll face it anyway.
Okay.
You can put a black background or anything.
Right. So going back to our original picture. So when talking about a bus, this is a picture of a broker. The thing in the middle that is doing everything. And that there's no communication without it. Concept of a bus, quite different. Main idea is we have some level of API, exposes a certain protocol. It says, this is the language of the bus. This is our agreed upon protocol. And as long as you respect the protocol, the bus can assist you in communication. There is the need to identify things by what they stand for. This color coding scheme. The fact that two things are deployed to the same box does not mean that they're the same thing. The fact that two things are deployed to different boxes doesn't mean that they're different. So what we'd expect to have happen is when the bus receives a message that says, this needs to go to green, then the bus will be aware of all these green boxes and say, I'll pick one. I should probably pick one that's free. It's not busy doing other things, but I'll pick one. Or when a message arrives that's addressed to purple, I'll say, okay, I'll pick a purple box and route that message there. Now, purple and green may be on all the machines or only on some of them. But when we're talking about routing, the routing is first and foremost to which color? Who should I send this to? To which color? And then the second question, which is what the bus answers, which of the boxes that I know are in this purple farm should I divert the message to? So the bus gives you that load balancing capability already in there. But what it tells you to do, you gotta color code your things. You need to give them different semantics. Without that, you actually can't communicate. So ultimately, when we're talking about NServiceBus, there is the part of NServiceBus which is the API. What you reference in your code. So when you compile your project and you say, okay, bus.publish, one of your messages, that's the bit that goes in here. Just like in Ethernet, you have a bunch of switches or routers that are behind the scenes that make sure that all the packets go to the right places. There is something else in NServiceBus that is the load balancer. Says, okay, you told me to publish this, and I know that purple is subscribed to the events that you've published. I'll go load balance between the purples. And there's a load balancer as a part of the bus. For those of you looking for what is the load balancer in NServiceBus, show it to you really quick. So after you download it, as a part of the processes, there it is, number one, distributor. It's part of NServiceBus, another process that you run in your environment says, I'm going to load balance stuff for you. So that you don't need to think about where things are deployed. If you want, put them everywhere. Right? Why not have anything run anywhere? greatest deployment flexibility. And I'll just pick the free one. What you end up doing, you run one load balancer per color. Okay? So each color in here gets its own little load balancer. And what you need to do is you need to use that name. You color code the load balancer as well. Say, this is the load balancer for purple, and this is the load balancer for green. And anybody that needs to say anything to purple should actually talk to the purple load balancer. Just like any browser that wants to talk to your website is told, go talk to the load balancer. He'll forward your request to the appropriate box. Exact same thing here. And Mark would like to do something.
I was just going to ask what happens if the load balancer goes down, because that seems like a single point of failure.
Right. What happens if the load balancer in your website goes down?
Stays on the queue and
I'm saying in a standard website. If your load balancer goes down, then your browsers aren't able to connect. And that's why we make sure that we set up our load balancer technology with failover. And you do the exact same thing with a distributor. Say, I'm going to put this on a highly available box, like a Windows cluster, so that if one of them goes down, it'll fail over to the other one. Okay? Now again, there's no assumption about where our load balancer is. We're going to have to, just like the network engineers, decide where we put this stuff. But from a logical perspective, saying there's a purple load balancer, there's a green load balancer, and ultimately it is the one that picks which machine to distribute things to. So that's the idea of the physical one-to-many communication, which is another slight difference from a lot of the assumptions that people have. When hearing publish subscribe the first time, one of the things that sort of jumps to our mind is, okay, so we're going to have this machine and it's going to publish to those machines. So they think about publish subscribe in a very physical sense. Take data from one box and get it to a bunch of other boxes. When actually what could be the case, say green is publishing something that purple is subscribed to. And it could ultimately just do this. Publish subscribe does not necessarily indicate that there are many things on the other side, or that the things on the other side are physical. All that it says is, somebody said that they wanted to be notified about this event, and we want to get that message to them. There could be only one, but what is significant is that we're talking not at a physical level of distributing stuff between machines. We've got load balancers for that, right? You get a message, pick a machine, transmit it here, there, and ever. Load balancers give us the ability to fan out communication across multiple machines. Publishers and subscribers are there to talk at a different level of abstraction. It says, I'm the sales service, I'm green, and I'm going to publish order accepted. And then the purple service over here that says, I'm shipping, I'm interested in hearing about orders that are accepted. It's that kind of communication that we're talking about. Logical publishers making statements of fact, and logical subscribers doing something when that information arrives. We may have more than one logical subscriber or just one. But it's not, publish subscribe is not about distributing a bunch of messages between a bunch of different machines. And that's where a lot of people start out in the wrong direction when using NServiceBus, saying, oh, okay, so the user clicked a button, I'm going to publish a create customer command. Why? Because I want lots of machines to see this. That's the wrong way to look at it. Because creating a customer is not an event. Because there can be somebody at the other end that says, sorry, duplicate email address. Customer wasn't actually created. In a true logical publish-subscribe communication, a subscriber can't undo the event. It can't say, no, the customer wasn't created. So when thinking about the communication patterns, keep that in mind. It's a different kind of communication that means a lot of things. One of the things that it means is that not everybody can publish every event. Well, an example of that, it says, in a given retail chain, there's a certain department, the pricing department, that gets to decide how much things cost. So they say the price of bananas next week will be $1 per, or whatever it is, 50 kroner per kilogram. Now, if I walk into one of those retail chains and I go to publish the exact same event, so I walk into the store and I say, the price of bananas today is 2 kroners a kilogram. Somebody else says, who are you? You don't get to say that. We're not going to listen to you. You don't have the responsibility to make that statement of fact. And it doesn't matter if I push the manager out of the way and stand on the exact same floor tile as he did. Doesn't change that. Doesn't matter that I'm in the same machine as the other guy is. Responsibilities are logical. And as a result of that, there can only be one color, only one logical service that publishes a given type of event. And because we have the ability to have multiple instances, we don't have to worry about scaling out and all that kind of stuff. Because often when people are trying to get NServiceBus to work, they're mixing up, physical scaling things out and load balancing stuff and publish, subscribe, and trying to juggle too many concepts in their head at the same time because they're not exactly sure what is a service bus. In a service bus environment, you get only one logical entity that gets to publish a given type of event, which makes it very clear to whom to subscribe. If there can only be one department in the organization that tells us what the price of bananas is, we know where we go to subscribe, because there is only one color, there is only one thing which gets to make that statement of fact. And all of the NServiceBus design, all of the NServiceBus configuration that we're going to be seeing in a bit is going to be reinforcing that fact. If you are trying to design your application in a way that does not follow those rules, NServiceBus will make it hard on you. Because you're trying to use it as something other than a service bus. So for those people who are just starting their evaluation of NServiceBus, and it feels like it's hard going, I recommend you stop a second and go back to a logical picture and say, how do I divide up the responsibilities so that one thing and one thing only can publish a given type of event? After you've drawn that picture on your whiteboard, come back to NServiceBus, and it'll all make sense again. Okay? Any questions at the conceptual level so far, before we drill into the more nuts and bolts stuff? How about other examples of publish subscribe? Give me an example of publish subscribe. I'll write them down here. Logical pub sub. Now it's your turn. I know in Norway it's a little bit difficult. Publish subscribe. Those people who are using NServiceBus on a real project. Give me an example of some publish subscribe that you're doing. Price feeds. Okay. What is it about a price feed that makes it an event? Okay, so what is the event? What logically does it represent? Now, the price of a product now is X. Okay, so the event is, what is it? Product price updated. Now, this is a very good example because it allows us to look at certain assumptions that we might have had in a synchronous kind of architecture as opposed to a loosely coupled architecture. In a standard synchronous architecture, everything happens one after the other. There is a clearly defined first A, then B, then C, then D. And there will, under no circumstances, A run after D. If you specified first A, then B, then C, then D, A will be before D, because the WCF calls work that way. When doing messaging, when doing publish subscribe, if I publish one after the other, the price of bananas is $1, and immediately afterwards I publish, the price of bananas is $2. Your impression is that everybody will get the second event after the first, because that's how it would happen in a WCF world. You would call everybody saying the price of bananas is $1, the price of bananas is $1, the price of bananas is $1, and only after you completed talking to everybody would you say the price of bananas is $2, the price of bananas is $2, and that way you would know that things happened in sequence. However, if we're in a kind of world where some of you are listening, some of you aren't, I run into the room and I say, "Psst, the price of bananas is $1. And some of you overhear that and say, what? Someone said, what? Did they say the price of bananas? I wanted to know the price of bananas. Right afterwards, I run in the back door and say, "Psst, price of bananas is $2. The information starts propagating the other direction. The price of bananas is $2. I said, I just heard it was $1. I said, are you sure? When did you hear it? I don't know. What time have you got? Oh, I'm still on New York time. Shit. Are they in daylight savings time or not? So is it $1 or $2? And you see these events kind of crossing. What time did you receive it? Are you sure? When did he send it? I don't know. I heard about it 5 minutes ago. When did you hear about it? I also heard about it 5 minutes ago. What is the price of bananas? Our assumption that things will always happen in sequence break down in a parallel asynchronous world where we can't ensure that everybody will be online and listening at exactly the same time. And not only that, but they are operated in a single-threaded fashion, so that even if the messages arrived in the queue in order, that the threads didn't process them out of order. When thinking about publishing events, especially when there can be continuous updates, we need to take into account the fact that not always will things run in the order that we think. They may arrive in order at some partners, and they may arrive out of order in other partners. They may arrive in order at some partners and be processed in a multi-threaded way out of order. Therefore, as a publisher, I need to be a little bit more specific about the semantics. When I say the price is updated, it's not updated from now until the next time I tell you. Say the price of bananas will be price from 2. And as a publisher, it becomes my responsibility to make sure that anytime I'm publishing an event, it's at a different duration. We don't get overlaps between these things. There's a lot greater responsibility on publishers when they're making statements of fact in a parallel world. NServiceBus can't magically solve this problem for you. If you didn't think about this kind of stuff, about things running in parallel, about the fact that not all machines may be up and running at the same time, that the machines may be running in a multi-threaded way, you may run into a lot of trouble with remnants of your synchronous mindset. And it takes some time for that to go away. So anytime you're starting out this approach saying, okay, I'm going to publish an event, ask yourself that question that says, what if they get the next event first? What if they're processing them at the same time? Semantically, how do we protect ourselves? So it's not just technical pub/sub that we're talking about. We need to make sure that the semantics are taken care of. And in the case of a price list or a price feed, there is that metadata information that says, what is the validity of this price list? Now, in the case where you didn't get that information, now you're in trouble. Now you're saying, I've got a price list, and I want to publish the next one. But, what if somebody didn't receive it yet? What if somebody was offline when I sent the first one, and it's still waiting in their queue? As a publisher, I can't know. So if I send out the next one, and they wake up, they may process them in the reverse order. So a lot of events that you'll be publishing in a service bus kind of way will have this, if not a to field, they will definitely have a from field that indicates, what came first. Because you as a subscriber can't assume that events will arrive in order. Other examples of events. Capture finished, like a screen capture, or cab? A cab ride. Okay. Okay, cab ride finished. Can you give me an example of a subscriber to that event? A database updater sounds like something that is technical in nature. In other words, let me ask you this question. Okay, but I want to spend a little bit of time talking about that scenario because it's one of the cases where you might have introduced some publish subscribe at a place where you might have done some RPC ADO.NET kind of save this over there. So you're saying, okay, cab ride finished, but until it's written in the database, is it really finished?
Yes, because it's finished from the external system.
Well, keeping in mind that we're talking about logical statements of fact and not so much physical, which integration was involved. Inside our world of green, we could have done client talking to server, talking to third-party system, getting response from third-party system, calling legacy application, getting a response from a legacy application, writing it into my local database, all of this in the land of green. Until I finally say, I'm done. Statement of fact, cab ride finished. And there is nobody on this planet that can say, no, it isn't. So any kind of integration that's involved will be happening within a color. And the publish only happens at the end, after all integrations are completed. So in that case, what we'll tend to see is something like this. Where we may use inside our land of green other orchestrations engines that say, I'll first save it to this system, get an ID from that system, put both of these IDs together in this system, call that web service. When it returns back a success, we have to do a fair amount of orchestration in our land of green before we go and publish an event. So the places where we do integration, rarely will there be publish subscribe involved. Because I know who I'm talking to, right? This is client server, this is tightly coupled orchestration, that until this entire process completes, I can't make a statement of fact. This is very different from what people are used to, because we tend to assume that a service bus can be used anywhere that web services or WCF communication is used. We tend to assume that they're for the same thing. They're not. If you need to do orchestration, tightly coupled orchestration, you need to get a response back from another system to know that something's actually been successful. Don't use publish subscribe for that. You may be able to use some one-way messaging. You may be able to do that, and we'll talk a little bit about that later. But it's not a publish. So only after all integrations with all third-party systems are complete, only then do you publish. The cab ride is really finished. The cab ride is finished. The person's paid. They've taken all their luggage. They're out of the cab and gone. That's it. End of story. What's that? Could be. I agree. I should have made it even harder for you to use it wrong. But that's kind of the thing. Trying to when talking about events, when talking about publish subscribe, the semantics there need to be ironclad. You can use NServiceBus for the purpose of integration, but then usually we'll be doing it as a kind of orchestration instead of something like BizTalk. But in that case, we'll often be doing bus.send and bus.reply. We're going to be using the one-way messaging for its technical properties, but at that point in time, it'll be more message broker in nature for the purposes of getting durable communication, for the benefits of transactionality. So all the technical reasons why NServiceBus is useful can make it useful for that kind of orchestration as well. However, in those places, we will tend not to do publish because, well, somebody else might subscribe to that, and then later on we say, no, just kidding, the cab ride wasn't actually finished. Now the guys from billing need to say, oh shit, now we got to go roll back our transaction, and the guys from somewhere else, we start to get into a more difficult scenario of compensating transactions for subscribers. We don't want to get into that. Yeah, you had a question back there. Mm-hmm.
But let's say you want to introduce some reporting in this command. So you have a two-step process.
Mm-hmm.
Maybe you have a trade which is initiated and then it's executed.
Mm-hmm.
So you want to report immediately after it's initiated.
Okay.
So I'm thinking, okay, then I have to publish an event. But actually, the process is telling this other thing to execute it, you know? So
Okay.
should I do the PubSub because I want to introduce some extra reporting and stuff real time, or did you?
Okay. So I think the question that you're referring to is related to command query separation, where a lot of people have seen the events that are in there. That relates to, so the question was, In those diagrams, we often see that the command side is publishing an event that is subscribed to by the query side, by the reporting side, which ultimately changes its reporting model off of the back of that command. So while we can, so the fact that you said in the case of a trade was submitted or was it initiated, and then we have a second step which says the trade was processed or accepted as a second step. We may have multiple levels of granularity of events. So we may use some command query separation inside here where we say, we're going to publish an event, but this is our own event. We're not going to let anybody else know about this event. It'll be our little secret that we're talking to each other about. And only when a trade has been fully accepted will we turn around and tell to everybody else, oh, we've got a trade that was accepted. And after a trade was accepted, we're not going to change our mind and say, oh, no, sorry, it wasn't. Whereas when the original trade was submitted, say, well, the trade was submitted, okay, but we're still not sure we're going to do it. So if you are going to be doing that kind of command query separation or making use of events to update a reporting store, it's often going to be within a color rather than between these logical colors. Okay? So the guys over here are making signals, say, break, break, break. So we're going to take a quick break.